Let me introduce our speaker today. It's a pleasure to have Daniel Slichter with us. He's from the Ion Storage Group at NIST in Boulder, Colorado. And he did his undergrad work at Harvard University, finished it in 2004, then did his MA at the University of California in Berkeley, and his PhD also at Berkeley, which he finished in 2011. And his PhD research was on superconducting quantum information, where he performed the first continuous high-fidelity state readout of a superconducting qubit and looked into quantum feedback, measurement back action at near quantum limited parametric amplification. He came to NIST in 2012, where he first worked as a postdoctoral fellow and then subsequently as a staff physicist. He's the recipient of a Hertz Foundation Fellowship, the Hertz Foundation Thesis Prize, and an NRC postdoc fellowship. He's a senior member of IEEE and currently serves as an associate editor for IEEE Transactions on Quantum Engineering. His recent research on trapped ions includes laser-free entangling gates, strong unitary squeezing of trapped ion motion to enhance quantum sensing and to effectively enhance the ion-ion interactions, and the present detector work that he's going to be talking about today. Before we start the talk, just a few words about the mechanics of how this works. We'll listen to the talk, and if you have any remarks that you would like something is going wrong, you can't hear the speaker anymore or something like that, use the chat window. And in the end, we'll take questions. And for that, afterwards, you're invited to use the Q&A window, which is in the Zoom bar at the bottom. And if you want to ask questions, you can already do that now, but we'll look at the questions at the end of the talk. So again, thanks for being our guest today, and we look forward to your talk.
Great. Well, thank you very much, Christian, for the introduction, and thank you to you and all of the organizers for giving me the opportunity to be here today and present this work that we've done in our group on ion trap integrated superconducting photon detectors for qubit readout applications. As mentioned, I'm Daniel Slichter from the Ion Storage Group in NIST in Boulder, Colorado. This is work that was done in collaboration with many people. I want to highlight two in particular. Varun Verma is a staff scientist in the faint photonics group at NIST and is a world expert on superconducting nanowire single photon detectors. And he and I have been working very closely on this project for many years now. To get it to this stage. And secondly, I want to point out Susanna Tadaro, who is a graduate student now, a postdoc at MIT, who did all of the heavy lifting, taking data, doing the ion trapping, et cetera, like that in the lab. And then Katie McCormick, Jonas Keller, David Alcock all contributed to the setup and preliminary measurements in a number of important ways. Andrew Wilson, Dave Wineland, Sewu Nam, Rich Mirren, and of course, Didi Leibfried are staff scientists at NIST who've all been very involved at various stages of this. And many of them actually came up with some of these ideas of how to do this before I even joined the group, and then said to me, hey, here's sort of an idea we had. Would you care to run with it? So here's where we've been able to run with it. I will start off by giving here's sort of an outline of my talk. I'll begin with a little introduction and a description of ion fluorescence readout, which is what we'll be talking about today. Then I'll describe some basic properties of these superconducting nanowire single photon detectors. Then I'll talk about the ion trap that we've made with these integrated detectors. I'll describe the results and the various sort of ways that we've measured the performance of this system. And then I'll present some conclusions and future outlook. And again, please, if you have questions, put them in the Q&A, and I'll be excited to answer those at the end of the talk. So we'll start with our introduction. So trapped ions are a really wonderful quantum playground. There's all sorts of things that you can do with them. You can do quantum computing and quantum simulation tasks. You can do quantum enhanced sensing of various different quantities. You can use these sort of quantum logic techniques that are often seen in quantum computing and stuff also to do things like spectroscopy on interesting species like highly charged ions or molecular ions even, and really sort of extend the capabilities out to more exotic species using these sort of quantum techniques. And finally, frequency standards, some including this here, which is the aluminum ion quantum logic clock, rely on quantum technologies and quantum control to be able to drive forward the frontier of frequency standard technology. So the question is, how do you play on this quantum playground? What are the tools that you need? And basically, one good way to sum them up was given by David DiVincenzo about 20 years ago. And these are known as the DiVincenzo criteria. And these are basically the requirements that you have to have for quantum computing, or for a lot of sensing and clock applications as well. There's some of them may be a little relaxed for those. So the first thing that you need is you need stable qubits that you can isolate. Well, we have no problem with that. You can trap atomic ions for minutes to even month time scale, depending on how your trap is designed. You need the qubits to be coherent, to maintain quantum coherence, phase coherence in quantum superpositions over long times. And for trapped ions, coherence times can be seconds. There was a very exciting recent measurement from Ki-Wan Kim's group where they measured coherence times of an hour using dynamical decoupling. So we've got that one. You need to be able to initialize into a particular state. And this is generally done with optical pumping, which can prepare the electronic state in a certain state, and then also laser cooling, which allows you to prepare the motion of the ion in a specific state, usually close to the ground state of motion. Then you need a high fidelity universal set of gate operations. So this is basically being able to control the quantum state of one or multiple qubits in an arbitrary way. And trapped ions do quite well right here. These are leading numbers for any quantum technology, actually, where you can get single qubit gate errors at around 10 to the minus 6. Error per gate, and 2 qubit gate errors where the error sort of ranges around 10 to the minus 3 per gate. And these involve different technologies. This involves microwaves. These first two here involve stimulated Raman transitions. This involves near field magnetic field gradients, and this one involves a far detuned light shifting laser on an optical transition. So there's many different ways in which one can realize these gate operations. And then finally, the fifth criterion is one needs high fidelity individual measurement or readout of qubits. You need to be able to see a qubit and measure its state with high fidelity particularly. And that's what I'm going to focus on in this talk here. And with trapped ions in quantum computing and quantum sensing and things like that, one typically uses fluorescence readout, which is also known as electron shelving, which has been proposed many years ago by Hans Demotte, and is a real workhorse of these technologies. I also want to point out, though, that there are many people probably listening in who are familiar with methods that don't involve lasers and fluorescence, like using magnetic gradients to do spin to motion conversion, and using electrical tank circuits to read out the state of an ion as a result. And this is often used in cases where fluorescence readout is not possible, either due to optical access or lack of suitable optical transitions that one can access easily. So let's talk a little bit more about trapped ion fluorescence readout. And I'll use the example of beryllium here because the work I'm describing is done with beryllium ions. So in beryllium, the ground state basically has two manifolds. I'm just drawing two levels here. There's actually more, but there's a cartoon that are split by a microwave frequency. And then there's an excited P state where the transition is in the ultraviolet. For beryllium, it's 313 nanometers. And the way you do fluorescence readout is if you are in the down state, you drive a laser that's resonant with this transition, and the polarization and frequency are set in such a way that once you excite to this P level here, you can only ever decay back to the state that you came from. And so you'll go around and around and around in a closed fashion. This is known as a cycling transition. By contrast, if you're in this other state, which is detuned by over a gigahertz, the laser is not resonant with anything up here, and so you won't actually drive any transitions. And so how this manifests is that if you're in the down state, the ion will basically scatter spontaneously photons in many different directions. Whereas if you're in this up state, the ion won't scatter any photons. And you can actually see this on a camera. If you have a camera and you take an image with a microscope, you can see a little glowing dot. This is a fluorescing ion. And you have to believe me here that there's actually an ion there, but it's not fluorescing. But you can't tell because there's no light coming. So typically, this fluorescence results in about 1 million or 10 million photons per second scattered into 4 pi, into the sphere. And it is sufficient to basically count approximately 10 if you're in the bright state, assuming the dark state is quite dark, in order to be able to determine the state, whether the ion was fluorescing or not, just from the number of photons you've counted. And this is based on the fact that the number of photons you count will be Poissonian distributed. So this is beryllium. It's at 313 nanometers. There are other ions, and I'll just, for those who are not familiar, discuss the readout wavelengths there. That for magnesium, it's 280, 369 for ytterbium, 397 for calcium, strontium 423. So these are all wavelengths that are in the ultraviolet or in the blue. And some of these species also require an infrared laser to repump during this in order to close the cycling transition. So now we have these ions that are fluorescing. How can we hold them in place in a trap so that we can do interesting quantum things with them? There are different ways, but the method that I'm going to talk about today are what are called linear RF ion traps. And so if you have a charged particle, it's not actually possible to confine it in 3D space using just static electric fields. This you can look at the Laplace equation and convince yourself of this. But it is possible to have a dynamical confinement if you have oscillating electric fields. So a linear or Powell trap, linear RF or Powell trap is classically done in this sort of 4-rod geometry, where if one looks end on, you have an RF voltage on these electrodes and then ground or a DC voltage on these ones. And this gives you a quadrupole right here at the center. And so the quadrupole is confining in one direction and anti-confining in the other. But if you flap the quadrupole back and forth at a radio frequency, you can basically realize an effective confinement. If this oscillation is fast enough that the ion can't ever roll down the hill too far, you'll get a confinement. And typically, these RF frequencies are tens of megahertz or 100 megahertz and tens or hundreds of volts even. Now, one thing you can do with a trap like this, instead of making it in 3D, is you can actually sort of unfold it onto the plane. And when you unfold it onto the plane, you have reduced symmetry, but you still have this RF quadrupole. And this is convenient because it allows you to make this trap using microfabrication techniques. So you can make smaller features, more complex systems, etc. And why would you want to do that? Well, one of the big things that people are going for is scaling. And one of the more popular methods for thinking about scaling the trapped ion quantum computer is the so-called quantum CCD architecture, which is shown here in this cartoon picture. And so the idea is you have a large trap with confinement such that you have many different zones where you can confine ions. And you move the ions around the trap between these different zones. And the zones might be dedicated to readout of the qubit state, or just a memory to hold a quantum state, or you could do gate operations in some area. And you only have laser or microwave access for these operations to some subset of the trap. And then a system like this, you can basically harness microfabrication, like I mentioned, in order to make it large and complex. And this is a vision that was first pitched by Dave Wineland over 20 years ago. And many people have been working on it. So it's really, it's gone from this vision to a reality. There are many different kinds of traps made in many different ways, now even in commercial trapped ion ion quantum computers that follow this sort of general picture. So now, how do you do the fluorescence detection in an ion trap? As we mentioned, the atomic physics of it. Well, usually what one has is you have an ion, you shine a laser on it to drive this cycling transition. It emits photons, and you collect some fraction of them with some sort of high numerical aperture objective, and then you image them onto a camera or a photomultiplier tube to be able to count the photons. And as you're scaling up, you have more ions, and so now you've got more here. So so now the challenge is that now you need a high NA objective that works for UV light. It's got to have a large enough field of view to encompass all these ions. It needs to have enough magnification that you can resolve them. They're sort of 10 microns, 5 microns apart, maybe. You need low distortion. You don't want this ion's photons hitting this ion's pixels, because that will cause readout errors. So this is a tricky optical design problem. And then furthermore, as you scale, eventually you'll run out of room in the field of view. And then you run up against the issue that the diameter of such an objective is usually much larger than its field of view. And so if you just add a bunch of objectives together, you'll have these blind spots in between the field of view, which is, it's not the end of the world, but it's not great. And then there might be cases where you have limited optical access or even no optical access in order that you want to scale. So what would you do in that instance? And one possible solution is to actually use photodetectors that are integrated into the trap itself. You're microfabricating the trap. Why not put a photodetector in it? They would be self-aligned to the ion positions. They would have spatial resolution of the ions, and they could be potentially scalable. So the idea here would be something like this. You've got some ions, and they're above a trap, and there are different detectors that sit on this trap in these zones, and each one is responsible for collecting fluorescence in its own zone. And you only need to collect a few percent as described. And now you've got scalable trap integrated fluorescence readout. So there's been a lot of work that's been done in the literature on different ways of trying to do things like this. People have integrated optical fibers into an ion trap to collect the light from an ion. People have put micro-optics, mirrors or lenses into traps to basically collect some of this and bounce it out to an outside optic who doesn't need to have as stringent an issue. It doesn't need to have the high numerical aperture. People have mounted a trap on a photodiode and actually seen ion signals on the photodiode from fluorescence. Or you can put a trap that's fabricated on a high reflectivity mirror and use that as half of a cavity to collect ion fluorescence. So all these things have been worked on, and people have seen fluorescence signals, but high-fidelity qubit readout has not yet been realized with these kinds of technologies. Recently, there's been some work, and I'm highlighting here the groups at Lincoln Laboratory and Sandia on integrating silicon photodetectors into traps. And so these are single photon counting avalanche photodiodes, which you can see here. There's some detectors in the trap, and here there's a detector in the trap. And the dark counts are sufficiently low, and the quantum efficiency is sufficiently high that in this preprint here from Sandia, that they were actually able to distinguish between an ion and not an ion using the ion fluorescence with a reasonable fidelity in about 7 milliseconds. So this is very exciting. This is early days on this technology. This just appeared earlier this month. So I'm excited to stay tuned and see what comes of this. So now I'll move on to describing some basic information about superconducting nanowire single photon detectors. So the operating principle of these detectors, I'll describe briefly so that you have a point of reference. The detector consists of a small nanowire, so it's sort of order 100 nanometers across, through which you flow a static bias current, which is less than the critical current of the nanowire, so it's a supercurrent. It flows without resistance. And when a photon hits and is absorbed, it creates a local hotspot that's not superconducting, breaks Cooper pairs. So now the bias current is forced to flow around that hotspot. And if the bias current is, if the hotspot's large enough, the bias current in these regions is sufficiently high to exceed the local critical current density. And that drives these portions normal as well. And now you end up with a resistive bridge across the entire thing. So what was a superconducting wire is now a resistor. And so if you look at this in a sort of a circuit model, if you're driving a bias through this device here, it has some inductance. And basically, when it was superconducting, it was like there was a switch that was closed here. And now we can treat it as a switch that's opened. And instead, what you have is the resistance of this hotspot. So this current went from seeing no resistance to substantial resistance, and it seeks other places to go, and it will redistribute and go through this external shunting impedance, which usually is the impedance of an amplifier. And what you get is a voltage spike. So this is one we've measured in our lab. This is amplified. And then as this current goes elsewhere, this becomes superconducting again. The current returns with an L/R time constant, and this voltage pulse dies away. The detector has reset, and you're ready for another count. So the question is, are these detectors good for trapped ion fluorescence readout? Well, they do max count rates of over 1 million counts per second typically, so that's plenty for our purposes. The active areas that are achieved, there's tens to even some devices are hundreds of microns on a side, which is well matched with what we would like for our design. The system detection efficiency, which is basically I'll describe in detail later, is basically the quantum efficiency of the detector in a holistic sense, can be almost unity, has been demonstrated at telecom, and very good in the UV. This is still twice as good as the best UV PMTs and can be optimized more. The dark count rates can be very, very low for this. This is much lower than would be necessary for our purposes. The jitter can be, again, extremely low. Again, this is less critical for ions, but it's very exciting research in and of itself. It's tolerant of magnetic fields, and by magnetic fields, I mean in-plane fields up to 5 Tesla have been demonstrated. So those of you who are penning trappers, take note. So this means that we don't have to worry about the fact that usually there's a magnetic field in ion trap experiments. They can be operated, and some of them can be operated near 4 Kelvin, which is much friendlier for ion traps. You don't need fancier cooling stages which don't have as much cooling power. And then finally, the readout and bias electronics are fairly straightforward. And then a huge reason is there's a world-class superconducting nanowire single photon detector group right at NIST down the hall with whom we can collaborate, which makes this fantastic. I want to point out that there was very nice work done by the Duke group, Jung-Sang Kim et al. Stephen Crane was the lead author, where they basically used a fiber-coupled SNSPD instead of a PMT. They had their big collection lens, but instead of sending it to a PMT, they sent it to an SNSPD, and they were able to get very nice high-fidelity readout in very short time because of the excellent properties of this detector. So the way that these detectors work, you can look at the performance as a function of the bias current that we flow through. So you remember you have to flow a bias current through the detector in order to get it to click. So below a certain level, I'm plotting here in this upper panel the total system detection efficiency, which is defined as the number of electrical clicks that we count divided by the total number of photons that are incident on the device. So it's the full quantum efficiency from start to finish. At low bias currents, we don't see clicks. The hotspot is not large enough to make the rest of the current drive the nanowire normal. And then above some level, it starts to rise, and then there's sort of a plateau in the efficiency here. And you see it's about 75%. This was done at this temperature and wavelength here. The dark count rates, this is in count per second. This is a log scale. These tend to rise exponentially as you get near the end. But just a little comparison, this is sort of a very state-of-the-art photomultiplier tube at this wavelength. So you can see that in this whole range of bias currents right here, you have better quantum efficiency and lower dark counts than a state-of-the-art PMT. So these are very nice photodetectors, even for the UV. But there's some questions about integrating these detectors into a trap that one has to ask. First of all, what about this trapping RF? Remember, we've got this sort of few microamp bias current in these detectors. And then the trap RF is tens of volts at tens or hundreds of megahertz. That's a huge signal going on this electrode right next to this detector. What will that do? Secondly, what about stray light and dark counts? There's no sort of optics to, reduce the impact of these coming on these detectors. This could be laser beam scatter, or room lights. What about crosstalk? What about this ion here fluorescing and hitting that detector? Do we have to care about that? What about the operating temperature? Can we get these detectors to run at the temperatures where it's easy to operate an ion trap? And then finally, what effect will these detectors have on the motion of this ion? In particular, will there be excess motional heating of the ion due to either exposed dielectrics, something about the materials, etc.? So now I'll move on to talk about the device we made where we actually have an ion trap with an SNSPD integrated inside. So here's a photograph of this trap. This is electroplated gold on a silicon substrate. And then right here, this little dark thing is an SNSPD made of amorphous polysilicon, which is a superconductor. This was fabricated in the clean room at NIST by Varun Verma and myself, and we've spent many, many hours working on many iterations of these designs and troubleshooting all sorts of things to basically bring the ion trapping process and the SNSPD process into alignment. And there's lots more work going forward to be done on this as well. So if we look here, you can see this is in this bow tie shape that was pioneered by Sandia to reduce beam clipping and thus stray light for laser beams that come over the trap. If we zoom in on this sort of central portion here and look with an electron microscope picture, it looks sort of like this. The pink electrodes here are the trapping RF electrodes. The green here is the SNSPD. And we have these gray control electrodes here that allow us to load and move the ion around to a continuous array of positions along this. So generally we load over here, and then we transport the ion over to the SNSPD and do the detection over the SNSPD. And so here is a cartoon of a laser beam coming in and then the ion fluorescing, and here's the detector which counts some of those photons. And the solid angle is such that the effective NA is about 0.32, or if you account for polarization, we collect about 2% of the photons are from the ion are incident on the active area. So the ion height here, the ion is 39 microns above this and 35 above the SNSPD. So it's not wildly unusual for surface electrode traps. And basically by having this arrangement we can transport, we can actually study how the ion behaves over sort of a normal trap portion versus over the SNSPD. And if you zoom in on the SNSPD even more, and this is a picture from a different device, but it's just a nice one to show, you can actually see this is this nanowire meandering back and forth and back and forth. And this allows us to take a very thin nanowire and cover a large active area by making it run back and forth. In addition, you'll notice that the trap electrodes around are actually quite a lot taller. They're 6 microns taller than where the detector is. And that fact helps sort of shield the detector from stray light as well, which is a nice feature. So one of the first things we did with this system is to characterize the performance of the detector with the trap RF on and off. And because you can't hold an ion with the RF off, these data were taken where we basically just shine a laser onto the trap or don't shine it for the lower panel and get the intensity about right, so we get count rates that would be typical of what we'd expect from an ion. So with the RF off, we see this shape to the count rate, or basically detector efficiency versus bias current. We don't count, then there rises, and then we have this large plateau as I described. And for the dark counts stay very low, and then they start to rise at the end. And again, this background here is just due to sort of room lights, but it's very low. It's not going to be a problem for ion readout. Once we turn the RF on, you'll see that the shape of this changes, but importantly, the detector actually still works. Even with the RF on, we can bias, say, here, and still count almost as well as we could with the RF off. Now, this trapping RF is 9 volts peak at 68 megahertz. This is a lot lower than a lot of other ion traps use, but we're able to do that because we're using beryllium, which is a very light ion. And I'll talk more about how we might be able to increase this later on. But so what is the impact of the trap RF on what's going on here? So first of all, you can see the best detection efficiency you get is a little reduced. It's about 17% less than what you could get without the RF. Secondly, you see that the maximum bias current you can apply before you drive the wire normal is reduced. So instead of being able to go to here, now we're only able to go to here with the bias current. But you can see the dark counts are still well behaved, and they rise as you get close to this maximum current again. But then you also see another thing, which is that this slope has sort of flattened out, and you can now count at bias currents where you couldn't count before, for example. So what's going on here? We can describe this with a model that takes into account the idea of induced RF currents in the nanowire. So I'm drawing here a cartoon picture of this system detection efficiency versus bias current. So it starts off low, rises, and then plateaus to this maximum switching current. And basically, what we think is happening is that we're applying a DC bias current at some value, but then the RF induced current is causing the bias current to oscillate back and forth at the RF frequency in the nanowire. And so that means that as a function of time, depending on when in the RF phase a photon hits, the detector might have a larger or a smaller current, so a larger or a smaller efficiency for counting. So even though here the DC bias current is such that you wouldn't expect to count photons, you might actually spend a fair amount of time in a regime where you would count them fairly regularly. And so that's why this would be higher than what you would see with the RF off with just DC bias current. So the RF is sort of providing like a self bias for this. Secondly, what you'll notice is once the DC bias current reaches a certain level, if you go higher than this, the RF current will exceed the switching current every cycle, and this will give you a dark count every RF cycle. And so now your dark counts go to 68 million counts per second, and that's no good. So this would explain why the maximum DC current you can apply would be reduced. And these RF currents are induced, as we understand, by capacitive coupling between the SNSPD and its leads and the RF electrodes. But so if we take this model and we actually build it up, we can actually do a fit to our data. And this is this blue curve. And you can see that the fit, which basically uses this green data as the system detection efficiency curve, and then modulates the current on it. This gives quite a nice agreement with the data that we have. So we feel that we understand probably what's going on with this RF pickup. So then the question is, what do we want to do about this? Eventually, if you could shield the detector or otherwise find a way to reduce the amplitude of the RF currents, you might get to a situation like this. And here, the point I want to make is you don't have to completely eliminate the induced RF current. You just need the magnitude of the RF current excursions to remain within this plateau region. And then basically, no matter where you are, you'll average a pretty good quantum efficiency. And it won't matter that you have this induced RF current in your SNSPD. So now I'll move on to talk a little bit about our experimental results with ions. So first, I will go over the relevant energy levels of the beryllium-9 ion for this readout. So here is the ground state with all its hyperfine glory. We have a small magnetic field to lift the degeneracy between these states. And this splitting, as I mentioned before, is a microwave frequency splitting. So now when we talk about the states bright and dark, we basically either prepare this state right here, which is going to be our bright state. And if you're in this state, and you shine on a suitably polarized laser with the right wavelength, you'll go up here to the P3 halves and decay exactly back to where you came from. The other state that we can prepare is this dark state over here, and this state, this laser is far off resonance, and so doesn't drive transitions. And I want to point out that if you look actually at this P3 halves level, there's actually 16 Zeeman sublevels here. And so really we're driving only to one of these levels, but these other ones are all around here. They're not very far detuned. So let's talk about sources of readout error in this system. So one source of readout error is what we call repumping, and that's when you prepare a dark state and it eventually becomes bright. And this happens due to off-resonant optical pumping. So even if you're in this state here, this laser's off resonance, but it's only about 1.2 gigahertz off resonance. And so there is a chance for you to off resonantly drive this transition, and then you'll decay down. And if you do that a couple of times, 2 times at a minimum, might be more, of driving and then decaying, you'll eventually optically pump into the bright state here, and then you'll start cycling. So this is what we call a repumping error. Then there are what we call depumping errors, and that's if you start in the bright state and you end up in any one of these other states here, which is not fluoresce. So not just this dark state, but any of these other states which are dark to the laser. And that can happen if this is not exactly sigma minus polarized. These other levels here are not far detuned, and so you could drive one of these transitions, and then it might be possible to decay to one of these other levels, and now you've gone dark. There's also, if they're magnetic fields from the trap RF, these can induce state mixing in these various sublevels, and then some admixture of another state gives you a chance to leave the cycling transition. So depumping and repumping are important to know about for what I'm going to talk about next. The next issue that I'm going to talk about is how we do our state preparation. So what we do is we prepare either nominally the bright or dark state, as I described on the previous slide, and then we perform this readout sequence that I'm showing here at the right. So the readout sequence consists of, first, we ramp up the bias current for the nanowire detector to its operating. It starts at 0, and before the readout, we ramp it up to its operating point, and then we leave it on, and then we ramp it down when we're done. And then we turn on the readout laser for 500 microseconds. And during that 500 microseconds, we'll get a series of random clicks from the detector indicating that photons have hit the detector. And then we have our pulse counter gated to basically look at all of these. And we actually record not just how many counts in this duration, but we actually record all of these arrival times with 1 nanosecond resolution. So we have the full story of when all of the photons arrive from this system. So the challenge here is that our ability to prepare these nominal bright and dark states is imperfect. The optical pumping's not perfect, et cetera. So our state preparation error can be on the order of or even bigger than the readout error that we're expecting. And so the solution that we've used is a post-processing solution. It's called heralded state preparation. And the idea is this. For every single run that you have where you've gated the pulse counter on and recorded the output of the detector, you take the first 50 microseconds of this, and we define this as the heralding period. So this is basically going to be used for state preparation. And then the remaining 450 microseconds are the readout period. And the idea is that we check each run during the heralding period. If there were no counts in the heralding period, we declare, aha, we have prepared state dark as of the end of the heralding period. So then we say, all right, here's our state prep at this time. If there were 8 or more counts in this, then we say, aha, we've prepared state bright. And if there's 1 through 7 counts, we toss out that run and we say, we weren't sure what state we prepared. But this basically means that when we go to start the readout here, we have a pretty good idea, an improved idea based relative to what it was before of what the state that was prepared was. And importantly, when we actually do our analysis of the readout fidelity, we are not using any of the data from this heralding period. It's strictly used to help us improve the state preparation fidelity in post-processing. So obviously in a real system, this wouldn't be how you did, but in this system where we're trying to get the best handle on the readout error, this is a helpful way to do it. I also want to point out that in the next few slides, I'm going to talk about varying detection durations and other detection things like that. This is all done in post-processing. So we basically have 450 microseconds of photon timestamp information. So if we want to do a 50 microsecond detection, we just look at the first 50 microseconds. If we want to do 100 microseconds, we just look at the first 100 microseconds of this readout period, and so on and so forth. So it's all the same data. We're just changing how much of this initial window of the readout period we look at for the analysis. So the first thing that I'll talk about is Qubit readout using the thresholding method, which is a very standard method that people use. And I want to here acknowledge that all of this heavy lifting in the lab, taking these data and getting the ions trapped and happy, was done by Susanna Tadero as part of her PhD work. So here I'm plotting on a logarithmic vertical scale two histograms, a histogram of heralded bright in blue, heralded bright in red and heralded dark in blue of the counts. And basically one can draw a threshold right here between them, where you say, all right, above this threshold, I'm going to declare that I think the state is bright if I count, 6 or more photons. And if I count 5 or fewer photons, I'm going to declare that I think that the state is dark. So these distributions here, the blue and the red, they're approximately Poissonian distributed. This is a logarithmic scale, but you see these tails here. There's a blue tail here where we prepared dark, but it ends up having more counts. There's a red tail where we think we prepared bright, but it ends up having fewer counts. And these tails are due to these depumping and repumping effects. They're not due to some feature of the detector itself. And so this is important to realize that sort of the limitations on the readout are when you prepared bright, but it ends up these red data here on the wrong side of the threshold, or you prepare data dark and it ends up on the wrong side of the threshold. These are what cause the readout errors. And these are basically due to the atomic physics of beryllium, not to something about the detector itself. So what we can do is we can vary the readout duration, and we can look at basically what the readout error is, what fraction of the time do we get on average the wrong state relative to what we nominally prepared. And what we find is that out at 125 microseconds, we get a readout error of 1.2 times 10 to the minus 3 on average. And this is sort of the best we can do with this threshold determination. But there are other methods that can be used for looking at the readout fidelity, and one of them involves using the fact that we know the photon arrival times. And so this is something that was described in Chris Langer's thesis a while ago, and was put into practice in this paper from Oxford. And since then, many other groups have used this. But basically, the idea is that when you can see the photon arrival times, you can see repumping and depumping events in some sense. You can see if an ion is scattering a lot of photons and then stops, or isn't scattering a lot of photons and then starts. And so what you can do is actually do a Bayesian state estimation as a function of the time into the readout. And once you feel confident at a sufficient level that you've seen enough clicks to say it's bright, or you've seen enough no clicks to say it's dark, then you stop the readout. And this can give you a faster and higher fidelity readout, usually about a factor of 2 in speed and a bit of increase in fidelity. And this is in fact what we see here. So these points are now not set by how much time we go for, because each time trace, there'll be a variable amount of time that the readout has to last before we reach a confidence level of knowing what the state is in our Bayesian estimation. But basically, these are all like, how confident do we say we need to be before we say it's done, I've determined what the state is. And so with this, we can actually get our optimum readout error as 9 times 10 to the minus 4 mean readout error in an average of 46 microseconds. So this is very nice, and it's important to have a little bit of sort of context to know how this goes. So here's a very nice figure that came out in this paper from the Sydney group, and describing the different readout fidelities achieved with different kinds of ions. So we're plotting here the mean detection error on the vertical axis versus the readout duration on the horizontal axis here. So the work that I'm just describing you here is this data point right here with beryllium. This data point here is actually the work that I mentioned earlier with the fiber-coupled SNSPD. So the SNSPDs are playing a role in both of these points to help make things fast due to their high quantum efficiency. And basically all of these other data points here are with different ion species and different detection techniques. But I want to point out something, which is that this is fairly fast, what we've done in our work. The fidelity is not as good as some of these other ones, but all of these other data here used a metastable shelving, electron shelving. So this much farther detuned from lasers, and you're less likely to have depumping. And so as a result, we could take our result and say, what would happen if we had the same collection efficiency and quantum efficiency, but we were using calcium-40, which has one of these metastable shelves. And obviously, there are some considerations that calcium-40 would need higher RF, so maybe the detector wouldn't work. But for putting that aside for the moment, basically the point is that it's really the atomic physics here that are limiting the readout. If we had something where the atomic physics were more friendly, we'd be down here with this kind of detector efficiency. So the point is that the kind of speed and fidelity that we're able to achieve with this detector are really state of the art. This isn't sort of a cute trick. It's actually a competitive technology with others for high fidelity readout. I want to point out, though, that all is not lost for beryllium atomic physics-wise, because you can use quantum logic readout. And these are results that Stephen Erickson, a graduate student who's just finished his PhD in our group, is writing up right now. But you can use quantum logic techniques to read out the state of beryllium-9. And depending on whether you're reading out basically the bright or dark state, and I'll leave the details to the paper when it comes out, you can get detection errors that are considerably lower than what we've achieved here. The time is longer, but this is dominated by laser cooling times, and it should hopefully be possible with better laser cooling techniques to shorten the time here. So, so this just gives you a sense of where this work fits in with other high fidelity ion readout work. So now we can talk about a couple of other things that we've discussed, one of which is talking about the fluorescence crosstalk. So you have to wonder how many photon counts you're getting on your detector versus the ion position. So if the ion is here, if you start moving the ion away to different locations, how does this affect the count rate? And in other words, how far would you have to space detection zones apart so that you don't have this ion landing on the wrong ion's detector? And there's a couple of effects here to consider. One is as you move this ion farther away, there's less solid angle of fluorescence that hits the detector. And then there's another effect, which is that the detectant efficiency of the SNSPDs actually depends on the incidence angle and polarization of the light. And so we can actually measure this. So we did a measurement where we took the ion and we moved it up to sort of 2 ion heights away. And we looked at the normalized count rate, basically, of the amount of fluorescence. And these are these blue data. And if you just consider the solid angle contribution, you would expect theoretically this red curve right here. So you can see that the data show that just looking at solid angle doesn't fully capture what's going on. But if you actually do numerical simulations of what the system detection efficiency ought to be as a function of angle and polarization, then you can put that in and you get this green line, which agrees quite well with the data that we have. So this is exciting. It's actually the first experimental measurement that I know of that is able to detect this angle-dependent system detection efficiency for SNSPDs. Usually people just have normal incidence. And then the other thing that we can point out is that we're actually able to use techniques like this to calibrate the system detection efficiency of an ion that's right above the detector. So with the trap RF on, we can use the known atomic physics properties and geometry of the ion to determine that we have about a 48% system detection efficiency. So this is better than a PMT, even with the hit we take from the RF being reducing our detection efficiency. I'll talk about one more thing about this trap, which is motional heating rates, because a lot of people ask, what's the motional heating rate look like? So we have this trap right here, and we can transport the ion to different locations. And so we measured heating rates in a couple of spots. One we measured in this zone B, where it's above gold and sort of far from the detector. And then we also can measure in zone D, which is right over the detector. And the heating rates in general, I'll spare you reading out all the details, but these heating rates, sort of tens to maybe 100 quanta per second, are actually quite good given the ion distance and the fact that it's beryllium, which is a light species. And so one can basically ask, well, okay, these are at different frequencies and different ion heights. How do they sort of compare? Basically, if we assume some sort of frequency scaling and distance scaling for electric field noise from surfaces, and I won't go into details here, we basically think that the surface noise that's being generated from this detector is about 6 times higher than what you're getting over just the gold right here. So it's a bit higher. We don't know exactly why that is, whether it's due to the fact that there's different filtering on these electrodes or something about materials, but both of the heating rates that we measure are basically consistent with state-of-the-art heating rates in a trap operating at this temperature, given the mass of the ion and the frequencies. So the good news is that having this detector here does not mean that heating rates for an ion above it are crazy. But there is another effect that one has to consider, and that is motional heating from the detector counts themselves. So I remind you over here from this plot earlier, if you look down at 0 applied bias current, there's actually still some click rate with the RF on, even at 0 bias current. And that's just from this RF sort of self-biasing that gives some probability of having clicks. And I remind you that when the detector clicks, it makes a voltage pulse. And that voltage pulse is actually part of the SNSPD going up to a voltage and coming back down. So what that means is that every time the detector clicks, you actually have an electric field pulse that happens at the ion position. So you're kicking the ion every time you have the detector click. And so what we've learned is that if you have stray light, then that causes clicks, even with the bias current off, that can heat the ion. And the effect is fairly low, but if you're doing something like a stimulated Raman transition, where you can have a lot of stray light because these are high power beams, then that can cause heating that's problematic over the ion. So the solution would be either do your Raman operations not over the detector or shield the detector, and I'll talk about that again in a bit. I want to point out this is not a problem during readout, because during readout, the ion itself is absorbing and scattering photons, and so its temperature is dominated by what the laser detuning is of the readout laser. Is it Doppler cooling, or is it heating, etc.? So now I'm coming to the end here, and I'll just give some brief conclusions and a little outlook for the future. So there are a number of targeted improvements that we can think about now that we've demonstrated that this is a really interesting and viable technique. The first thing we want to look at is electrical shielding for the detector. Obviously, this would help make smaller induced RF currents, which would improve the detector performance. It would help mitigate this issue of motional heating from the detector counts that I just talked about. And then finally, and importantly, it might mean that we could use a higher RF voltage. And that may permit us to use heavier ions than beryllium, which I think is an important thing for this to be viable in the longer term. Another thing we'd like to do is to change the material that we're using for the detector to increase its superconducting transition temperature, TC. That lets us run the trap at higher temperature, and it also helps if there's higher RF dissipation on the trap, which is generally the case if you have heavier ions. We'd like to, if we can, in concert with these things, increase the width of the plateau in the system detection efficiency. And that basically allows us to tolerate more induced RF currents, which basically helps again with these tasks. And then finally, we want to start thinking about how you can do arrays of these detectors with more than one pixel, as we've talked about in our sort of scalability stuff. And there are questions about this, like how would you best multiplex the bias and readout electronics for this? So yeah, I'll quickly mention that, is that you, Christian? All right. So I'll quickly mention that that one possible application for this that goes beyond what I've discussed here would be if you were to make an ion trap and trap an ion and be able to put a detector up behind it. And interchangeable detectors. And now you're using this ion as a calibrated photon source, like what we did here. And this might be a way to do absolute sort of quantum referenced calibrations of detector efficiencies using trapped ions as a fluorescence source at interesting things. And this was actually done in the context of the fiber-coupled SNSPD by the Duke group. I also want to point out that there's possible visions for integrating these detectors onto another substrate that's separate from where the ions have the trap electrodes, and this may help ease the challenges of fabrication and also help with the solid angle of detection, because now you're not limited by what you're able to fit in between the trap electrodes. You can use this whole half space up here. And I think in the interest of time, I'll skip through some of these other things that I've had here, and thank you for your attention. This is the whole ion storage group in beautiful Boulder back in the days when social distancing wasn't a thing. And then these again are the particular people who've been involved in this work, and I really want to thank them for their hard work, and thank you for your attention, and I'll be happy to take questions.